Hello everyone, this is Dr. Daya Sagar Chowdary, Senapati, Assistant Professor, Department of Electronics and Communication Engineering, Aditya University-Surampalem. Today I would like to discuss about the concept r minus 1's complement and r's complement of signed numbers. Coming to the learning outcome, at the end of this course, student will be able to calculate r minus 1's complement and r's complement of signed numbers for binary arithmetic, also performing subtraction in different bases. So before going to r's complement and r minus 1's complement, so we have to analyze the binary addition. So for binary addition or any addition, we require two numbers. So for the two numbers, if we consider here decimal 2 plus 2, that is 4. This is simple in decimal. If we go for addition, that is 4 plus 4, we will get 8. So this is also simple. So 6 plus 7, that means here the digits are 2. Now we will get the result, that is 13. That means, so before example it is 0, but now in this example that is 1. That means it will occupy 2-bit representation. Here also 09 with 08, if we add these two numbers, we require two places, that is 2-bit representation, that is the addition is 17. So simply if we go for, that means decimal to binary, so 10 representation is in binary 1010 and the 6 representation is 0110. This is the representation for 6. Now if we add these two numbers, so 0 plus 0, that is 0, and 1 plus 1, that is 0, and the carry is 1. Now the 1 with 1, that is carry is sum is 0 and carry is 1, and 1 plus 1, that is sum is 0 and the carry is 1. So that 1 here the representation, so the entire result representation is in not 4 bits but 5 bits. That means one more bit is added. That means the two inputs are 4-bit representation, but the output is 5-bit representation. So anyway, here the two inputs are, this is the truth table for the 2-bit representation, that means 2-bit addition. That means here most of the time in binary we will add any two combination, that means 00, sum is 0 and carry is 0, and 0 with 1, the sum is 1, the carry is 0. That means 1 plus 0, the sum is 1 and carry is 0. And if the two inputs are high, that is 1 1, the sum is 1 0 and the carry is 1. So with the help of this simple truth table, we can add this particular operation. Now if it contains, try with the 4-bit representation unless stated. That means if any question will come that is clearly not represented, then we can follow with 4-bit representation here. Now here the same thing. So 1 plus 6 we know in decimal, that is 7. With the help of this binary, so 001 representation is 1, 110 is the representation for, that is 6, and we can add with the help of, this is 111, that is 7, the result is 7. So this is easy calculation. While coming to here, so if we observe again the 4-bit representation, two inputs are 4-bit representation, but the result is 5-bit representation. Here also the 4-bit representation input and 5-bit representation the output. So here if we go for this representation, all ones are the 4-bit representation, and here also the two inputs are 4-bit representation, but while coming to the output, it is a 5-bit representation. With the help of this truth table, we can simply add these two numbers. So this is very simple binary addition. Why particularly we are discussing about this addition means, so for addition with the help of the truth table, we can simply add two numbers. But while coming to the subtraction, so computers, any digital equipment, the problem is they don't do the subtraction part. So for that reason, they will do the second operand. So we call that one as a first input and second input. First input is as it is, it will take, but coming to the second input, it will take the combination, like it will take like the complement of that particular number, and finally it will add to the first number. So that is the operation that is done in the digital systems. So for that second number complement, we have to perform some operations. So that is the reason we are going for this r's complement and r minus 1's complement. So here before going to r's complement and r minus 1's complement, so here the first terminology we call that one as a 1's complement. So 1's complement representation, simply we call this one as a, see here we take one example. So 1001, this is the equivalent for, that is 9, decimal equivalent 1001. Now the ones complement is very simple. That means here if we flip from 0 to 1 and 1 to 0, that is the representation of ones complement for that particular number, that is binary number. So here the number is 1001. If we shift 1 to 0 and 0 to 1, that is our result, ones complement. That means 1 is shifted to 0, 0 is shifted to 1, 0 is shifted to 1, 1 is shifted to 0. So 0110 is the ones complement of 9 in this particular operation, that is ones complement. While coming to the twos complement, this is simple. So here r's complement, so we will consider this as twos complement. So now simply the binary, the base, we consider this one as a base or radix. R represents the base or radix. For binary, that radix is 2. Now for the same representation, that means for 9, 1001, so this is the ones complement plus 1. That means here this will take r minus ones complement plus 1. So plus 1 minus 1 gets cancelled and we will get the r's complement. So likewise we will calculate. That means before going to r's complement, we have to calculate r minus ones complement plus 1. So it gives the r's complement. So this is the simple trick. We have to calculate the r's complement. Here also, so before going to the twos complement, we have to calculate the ones complement for this 9. So later we add the plus 1 to this particular ones complement, we will get the twos complement of this 9. So that is 0, 111. So with the help of the truth table only, we are summing these two binary numbers. So here other than the any number, so we can calculate with the help of r minus ones complement and r's complement. So here r represents the radix or base. So here for binary, r is equal to 2, base is 2. Most of the time we represent like this. And for decimal, r is the 10, that is nothing but we represent like this. So any number that is represented with 2 means that means base is 2 means that is binary, base is 10 means decimal. Likewise we are calculating. So most of the time this complement system is useful for the negative, representing the negative numbers. So we will check the operations also. So r minus ones complement, if we calculate r minus ones complement for any number, we have to concentrate on given number, we call that one as a capital N, that means representation capital N, radix is r, and total number of digits that contains the number, that means we represent with small n. So now this is the formula for that particular r minus ones complement. That means r to the power of n minus 1 minus capital N. That means here if we go for, let us consider one example. So if it is decimal, decimal contains the digit 10. So that means r is our 10. Next, so we have to calculate 10 to the power of small n minus 1 minus capital N. So this is the formula for representing the r minus ones complement for that particular operation. So we will check, that means how we can calculate the other operations also. Now coming to the nines complement for the decimal. So nines complement means here, so there are two type of methods here we can calculate. First of all, we follow the method 1. So for method 1, so the problem is the nines complement of 3454. This is the problem. So the given number is represented with capital N. So that means n is equal to 3454 and r is equal to 10. That means the radix is 10. Now n is 4. N is 4 means 3, 4, 5, 4. 1, 2, 3, 4. So likewise the 4 is the number. So the number of digits, that is representation. So now here the r to the power of, that means 10 to the power of n, n means small n, that is 4, here that is 4 small n, minus 1 minus capital N, that is capital N means the digit, whatever the given digit is, 3454, 3454, this is a digit. So we can simply calculate. So 10 to the power of 4 is 10,000 minus 1 minus 3454. So totally we can calculate 6545. This is the method 1. So this is the result for r minus ones complement. That means here that is the nines complement, because r minus ones complement in decimal is, that is nines complement. Now coming to, this is other problem for binary. So if we go for binary, we can take that 9 digit is not there in binary. So with the help of this problem, that means with the help of this formula, so we will proceed the operation. So here we can consider r to the power of n, that means r is here 2. So 2 to the power of 4 minus 1 and minus whatever the given data, that is 0 1 0 1, because here the given data is 0 1 0 1 and capital N is the given data and radix is 2 here in binary, and n is the, here there are 1 2 3 4 total 4 bit digit numbers. So that is why 2 to the power of 4, that is r to the power of n minus 1 minus the given data. So here 2 to the power of 4 is, so that is 16. So the 16 representation is 10000 in binary, minus 1 minus 0101. So this is the representation. If we subtract this one, we will get the 1010, whatever the result is there. So that means this is the representation of, so 1010, that is 9's complement for the binary. So this is the simple trick. So that means if we go for, if we observe this result, so r minus 1's complement in binary is 1's complement and r's complement in binary is, that is 2's complement. That means there is no 10 and there is no 9. That means if we want to calculate 10's complement and 9's complement in the binary, because there is no 10 and there is no 9 in the binary, that is why if we calculate with the help of the formula, then simply the results are like this. That means r minus 1's complement is, that is 1's complement result only we will get in binary, and r's complement result is the same 2's complement result only we will get in binary. So this is the important task. And next, coming to the r minus 1's complement for a decimal. So if we, this is a method 2, again we will take the same, that means r minus 1's complement. So we can take the given data, that is 3454, if we consider 3454, and 9's complement we can take, that means here the digits are 1 2 3 4, so 4 digit representation. So we can take the 9's complement number, that is 9999, because this is a 3454 4 bit representation. That is why we can simply subtract this number from 4 9's, we will get the result, that is directly r minus 1's complement result. So this is the one technique, that is method 2. And here for r minus 1's complement for binary is r minus 1's complement, that is here r is 2. So 2 minus 1 is, that is 1's complement. So if we calculate, so for, let us take one example, 5, that is 4 bit representation, 0101, that is 5. Now it is simply the flipping, that is 01. 0 is switched to 1 and 1 is switched to 0 and 0 is switched to 1 and 1 is shifted to 0. That means this is the 1010 is the final result. That means r minus 1's complement is the 1's complement for the digit decimal. So that means here we can also remove that 1111, that means 0101, we can remove from 1111 all ones also. So 1 minus 0, that is 1. 1 minus 1, that is 0, 1 minus 0, that is 1, 1 minus 1, that is 0. So likewise we can calculate with the help of this method too. So coming to the r's complement, so the given number is capital N, the representation is capital N and base is r and the number of digits is small n. So here the formula is r to the power of n minus capital N. So this is the representation formula for r's complement. Now for example, let us take for decimal. So r represents here, that is for decimal, that is 10, and for 10's complement, so we can calculate with the help of the formula 10 to the power of n minus n. This is the formula for r's complement for decimal. So now again there is a method 1 and method 2. So here for example, so if we consider 10's complement for 3454, we are taking the same number here. So 3454 is the capital N and r is nothing but the radix, that is 10 here, and small n represents the number of bits, that means 1 2 3 4 number. Now with the help of this formula, so 10 to the power of 4 minus 3454, this is the formula. Now 10 to the power of 4 is, so 10,000 minus 3454, so 6546 is the result for 10's complement. That means this is the r's complement representation. Now coming to for binary, so again r's complement means, that means again we are calculating r minus 1. So simply we can calculate with the help of this formula. So r to the power of n minus, that is capital N. So the given data is 11001. So now capital N is 11001 and small r is equal to 2 and small n is equal to 5. So now 2 to the power of 5, that is 32. So 1000000, this is the representation for 32 in binary, and this is the binary 11001, that is the given data. And finally, if we subtract this from this, so we will get the result is 00111. So this is the representation, that is 2's complement for the binary. Now r's complement, that is again for decimal, so method 2. So this method, so again we calculate the, so for 9's complement plus 1, for calculating the 10's complement, we can calculate the 9's complement plus 1 gives the 10's complement. So likewise also we can calculate, this is method 2. So the given number is 3456, the same number, and 9's complement we are calculating with the help of 4 9's, that means the given data is subtracted from the 4 9's, and that is the result is 6543. Now adding plus 1, so plus 1 gives the 6544, which is nothing but our 10's complement for this particular problem. So likewise here this is the representation r minus 1 plus 1, that is the r's complement representation, that is which is nothing but 2's complement for this particular binary operation. So same representation, so binary for of 25, that 5-bit representation is 11001, and 1's complement is this one, simply switching from 1 to 0 and 0 to 1, and 2's complement is simply adding the last digit, that means LSB, we are adding that 1 to this particular 0 will give our result 111. So this is the simple representation of r's complement for the binary. And so if we give on tabular form, so base 2 and base 10, r minus 1's complement is simply 1's complement, and r minus 1's complement for 10 is 9's complement, and r's complement, that is in order to add 1 plus 1, that is 2's complement, and here r's complement for decimal 10 is, that is 10's complement. So this is the simple trick for this calculation of this r's complement and r minus 1's complement. Now why these are used? Subtraction by borrowing is difficult and inefficient for digital computers. So because of this only purpose, we are going for this complementation method. Conventional addition is easy, implemented in digital computers. Addition is very easy for digital electronic gadgets, but the problem is coming to subtraction, it will take so much time for the taking the borrowing method. Using these methods are much more efficient to implement subtraction using addition of the complements of numbers. Simply we are complementing the second number and adding the complement to the first number gives the subtraction of that particular number. So r's complement signifies the subtraction. So this is the representation. That means if we want to subtract b from a, so simply we are calculating the r's complement of b and the result is added to a. So this is the trick for the following the operation of the subtraction in digital computers or any digital equipment. So here let us consider one problem. So problem 1, so subtract 6 from 13 with the help of 2's complement. That means here 13 6 representation, 4-bit representation, and 13 is also 4-bit representation. That means so we have to subtract 6 from 13. So 13 is the first input and 6 is the second input. That now we have to calculate the r's complement or r minus 1's complement for this particular 6, and the result is directly added to 13. So this is the representation, and finally we will get the result. So likewise, so if we calculate, because the question already given the 2's complement, so we have to calculate the 2's complement for this particular 6. So for 2's complement of 6 is, so 1001 1's complement, and if we add plus 1 gives the 2's complement, so that is 1010 is the 2's complement, and the 1010 is directly added to the binary 1101 gives the final result. So here the representation 6 is represented in binary, that is 0110 is subtracted from 1101. So here we are calculating the 2's complement for the 6 and simply adding the result to the 13. So this is the final calculation. So calculating the 1's complement for 6 is, this is the 1001, and adding 1 to the 1's complement gives 1010, and finally this 1010 is added to the a is nothing but here, that is 13. So this is a simple representation. Simply we calculate the binary subtraction in this way. So same, the problem is second problem. If we take subtract 9 from 4, that means here 9 from 4 means now the a is 4 and the b is 9 here. So again the representation, that means a is small number, b is large number. So now we have to calculate again with the help of 2's complement. That means before going to 2's complement, 1's complement we have to calculate and add 1 to the 1's complement will gives you the 2's complement. Here this is the 2's complement, and finally we have to add it to a. So if we add, there is no carry. That means there is no carry means, so the result is negative. So we have to keep this one in mind. So that means if there is no carry, the result is negative. So that is why keep that one in mind, that result is negative. And again we have to calculate the 2's complement here for the result. Again we will get the result. That means we will get the final result. So that is 5. So finally we will get the, so minus 5 here, the representation. That means if there is any carry, result is positive. If there is no carry, the result is negative. So we have to keep that one in mind. Likewise we have to calculate. And coming to the summary, this is r minus 1's complement and r's complement are used in digital systems to represent signed numbers and perform subtraction using addition, where r is the base of the number system. And the r minus 1's complement is obtained by subtracting each digit from r minus 1, that means 1's complement in the binary, 9's complement in decimal, while the r's complement is found by adding 1 to it, that means 2's complement in binary and 10's complement in decimal. So most of the time in computers, negative numbers are stored using 2's complement only because it simplifies arithmetic operations and hardware design. So thank you.